Let's examine an example of a transmission line with impedance conversion. In this circuit diagram, the source on the left has a source impedance ZS of 100 plus J 50 ohm and is connected to a load ZL of 50 plus J 50 ohm. And there is no transmission line connected in between. Our task is to determine the voltage on the load. Using the voltage divider rule, we can determine the voltage on the load. VL is equal to Vs times ZL over ZL plus Zs, and we get the phasor voltage on the load as 3.92 with an angle 11.3 degrees. Now, if we connect a transmission line between the source and load, the line length is 1/8 wavelength, and its characteristic impedance is 50 ohm. Our goal is to determine the voltage on the load. However, things become more complex as we cannot simply apply the voltage divider rule to find the answer in one step. Since the load impedance is transformed to a different impedance by the 1/8 wavelength line. First, we need to determine the reflection coefficient gamma 0 at the load end, where D equals 0, by calculating the difference between the two impedances divided by their sum. The resulting value is 0.447 with an angle 63.44 degrees. Once we have gamma 0, we can find the input impedance Zin, which is the impedance seen from the left side of the line to the right. Given that D is 1/8 wavelength, using this value, we can determine that Zin equals 100 minus J 50 ohm. Next, we can use the voltage divider rule at the left reference plane to find the input phasor voltage, which is 5.59 with an angle negative 26.57 degrees. After traveling 1/8 wavelengths to the load and combining with the reflected wave, we can get VL, which is V of 0 at the load end. In the end, the final answer for VL is 5 with an angle 45 degrees. When the load is not connected with a transmission line, we find that the input impedance is equal to the load impedance, which is 50 plus J 50 ohm. Meanwhile, the source impedance is 100 plus J 50 ohm. However, the imaginary parts of these two impedances do not cancel each other out. After adding the line and converting the load impedance to the input, it becomes 100 minus J 50 ohm. The source impedance Zs is still 100 plus J 50 ohm. When these two impedances are in series, their imaginary parts are eliminated, and their real parts are the same. This means that the two impedances are conjugate matched. So on the bright side, although the transmission line effect alters the load impedance, it is not necessarily a negative outcome. In fact, we can use the line to adjust the load impedance to achieve conjugate matching, which is crucial for maximizing power transmission. As a result, the transmission line is considered as an essential component and an effective tool for impedance matching in high-frequency circuit design.